Hopefully this is a good series of group reading sessions. The Graphics Codex. How would you describe the Graphics Codex?
I don't know. It kind of focused on offline rendering, I guess, but it's also talk about a bit of this and a bit of that, and it is also a good reference. After the main material, it have a lot of like just entries on different terms, what they means.
Yeah. Okay. So I guess we can get started. Just reading the first of surface geometry chapter. We skipped the C++ refresher and introduction, which is more just nice fancy words about the text rather than anything about graphics. So, okay. Light rays scatter or absorb when they strike a surface. Representation of surfaces is therefore concerned with supporting scattering, absorption, and interception rays. We'll model an object as a collection of surface, but for rendering we can ignore any of the other properties, such as mass or interior stuff. Anything that can't be seen is irrelevant. Yeah, that's a truth in rendering. Emperor has no. We can represent a surface by a pair of models, geometry and material. So the shape and the interaction with light of the shape. Precise definition. Implicit and explicit forms of equations for representing arbitrary geometry and triangle mesh representation. Raycasting chapter revisits the general. Okay, so then this chapter and the next couple of chapters only focus on the geometry and deal with that later. So, surface. Light is radiation. It goes through air and everything else, but then sometimes hits stuff. And then we can see that because it reflects off of it. So, but not all wavelengths are the same. I mean, that's a nice thing to say. Source propagates through a medium. So this speed of propagation of the light is given through medium. Chemical. Okay. So it's saying light speed of light is not constant. It depends on what medium it moves through. So vacuum, pure vacuum where there's nothing in it, no atoms, it's C0 and it's very, very fast. But if it's moving through matter like, human tissue or water or even just air, it's slightly slower than that. Hits the atoms and bounces around a little bit or just gets, slowed down by them. 1.3 times slower through water and 2.5 times slower through diamond. That's an interesting fact. So I think it's just trying to establish that light is a thing that is a physical thing, a physical physics thing. Surface, define a surface in general. Let the medium filling of volume of space be considered a homogeneous if light propagates at the same speed and is absorbed at the same rate everywhere in that volume. And when two different homogeneous media, we have an optical interface. When two media meet. Let's switch to math terminology. Optical surface is the 2D boundary between adjacent volumes of two different homogeneous media. So surfaces are oriented, single-sided. So there are always two surfaces on the top of the block of ice, the one facing upwards, where the light moves from air into ice, and one facing downwards, where light moves from inside of ice out to air. So it sounds like it's describing that surfaces are interfaces between different sections that are homogeneous. And we need to do that because light moves through media. And so, okay. And this is making sense to everyone so far?
Yeah, I actually never thought about surface in this way. I guess just I never thought of a surface as an interface between two media, rather
Right.
than yeah.
That's exactly my thoughts.
I guess it makes sense when you like look at the definition, or like, I mean, skipping ahead, but like when like everything's volume and everything's kind of transmissible, and like diffuse light is actually just subsurface scattered light.
Right. Okay, so modeling a 1D surface in 2D space. Surface mathematical boundary. The frontier of a set of points. Media exists in 3D volumes, so the boundary is a 2D surface. Set of points at the edge of the volume. So we need a mathematical model that is amenable to computation. Infinite number of points on a surface and of an interesting object, so we can't simply enumerate them all. Yeah, so let's go from, instead of having to think about 2D surfaces in a 3D space, let's just do a 2D volume with a 1D surface, which is much simpler to construct and think about. So 1D surface is a curve through 2D space. It's just the same idea, just less dimensions. And it's, the simplest surface in one dimension is a line. And so we have our classic algebra y equals mx plus b. At least I was taught algebra like this. I know some schools do it a bit differently. Kind of like this down here, that's what they teach. Regardless. Implicit equation, x is a test. We can substitute any point into the equation if the equality holds. And then p is the set of points on the line, is in the set of points. Oh, so you can put your x and y in, and if the equality holds, then it's a part of the line. Yeah, vertical lines do not exist in this equation. So yeah, this is more generalized and okay. So delta x times y minus y0 is equal to delta y times x minus x0. That's how I would interpret this. Yeah, where x1 and y1, x0, y0, two constants on the line p, and pxy is the point we wish to test. Yeah, you can get the y equals mx plus b by moving the things around and substituting. Okay. Oh yeah, the infinity problem is because if x doesn't change, then you're dividing by 0, and then that's undefined, or just not good math to have. Okay. Okay, so an explicit equation for a line is x0 plus x1 minus x0 delta x times t. This is, I think, that other form I was thinking of when I was talking about y equals mx plus b being the one I was taught. This is the other way to describe it. Yeah, t is the scalar value. So this is, I almost feel like this is a parametric equation.
Yeah,
but
it
maybe
is. Yeah,
okay.
we just put t and we get x, y back, right?
Yeah. So yeah, this we're starting to do. This is very vector-like with p0 plus p1 minus p0 times t. Oh, there's a big block of text here. Oh yeah, this is introducing vectors. So the difference of 2 points is called a vector. A geometric vector can be represented by a linear algebra vector, which allows us to leverage the machinery of linear algebra to operate on them. Very useful to have vectors. This equation is independent of number of dimensions. Yeah, because it doesn't say x, y, it says p, which is just a point in space. What else? 3, 4, okay. Okay, so this equation also, interestingly, doesn't assume where the x and y axes are situated in space. It's space independent, meaning your x and y axis could be inverted, like flipped with each other. They could be skewed. There is no, like, it doesn't have to be perfectly up and perfectly down and perfectly left and perfectly right. So
it'll always be just a line, though, right?
Yes. Like, the axis has to be that. And I think for this, math to be useful, the x and y have to be independent enough so that you can specify any point in 2D space with it. Because if the x-axis and the y-axis were parallel lines with each other, then you'd have nothing. Because you'd only have the single line, you'd be collapsed back into one dimension. If that makes sense. I'm rehashing my rusty linear algebra knowledge right now. So.
Yeah, and I guess if they're the same, like the x-axis is the same as the y-axis, it'll just be like lose a dimension, but still be a line.
I'm just gonna ask: has anyone listening here consider themselves complete noobs in linear algebra?
No, I understand this. I'm just thinking about whatever you put into T, it's always gonna hold. The T could be any number. It's just scaling whatever point is on that line. And
yeah.
0 and P1 are just any point in space, in 2D space.
Yeah. Just a quick aside, I believe this is very similar to the linear interpolation formula. And
I think it is, as long as T is between 0 and 1, right?
Yeah, I think it is.
So it's more like if T goes beyond 1, it means like the line goes beyond your second point.
Right. It's no longer the classic linear interpolation, and now you're extrapolating past it. But that's if you just don't clamp T properly. But yeah, it's a useful thing to be thinking about when you're looking at this description. It's a useful similarity. Okay, so triangle meshes to move on. So 2D triangle is the simplest polygonal surface. Okay, it's almost all computer graphics has been using triangles since as long as we've been doing computer graphics because of the nice properties it has. If you want to recreate a complex surface, you can do so with a bunch of triangles as long as they're high enough density to reasonably recreate it. It is the simplest polyhedra in it's a simplex. Triangle is the 2D instance of a simplex, which is the simplest polyhedra in some dimension. 3D simplex is tetrahedron, and I bet there's a 4D one that has an even fancier name, but the 1D simplex is a line segment. Triangle also the nice property also is planar and defines a convenient way to parameterize locations between its vertices. This is the one that I was looking for as far as why do we use triangles. Always planar. That's just a very nice property to have. And then parametrization of the surface based off the corners of or the vertices. That's super, super nice because you can describe any point within the triangle just as a multiplication factor. Is that the word for it? Of any of the corners. A 4D simplex is a 5 cell. I'm going to click that link. Okay, well, I guess this is our 3-dimensional projection of a 5 cell. Because I cannot see in 4D space. Interesting.
Quite confusing to look at, like all four of these things. I guess.
Yeah, because it's like this is a not 3D. This is a 4-dimensional shape that we're projecting into 3D to make it visible to us. It's usually how those 4D pictures work. The ones that are trying to show what it looks like. But because it's 3-dimensional projection.
3D and then project to 2D. Yeah, it can be really confusing.
Right.
Yeah. So this is what it looks like while rotating. It's just mental to think about. Yeah, anyways. Okay. So we can define a triangle by 3 points, and a point in C++ is most simply described by 3 floating point values. Okay. Yeah, this is just good enough C++ code for basic graphic stuff, 3 public variables for a point. Yeah, we'll have functions to define math operations later, I'm sure. Yeah. Okay. Immutable triangle. So you construct the triangle out of 3 points, and it's unchangeable. So you can access any of the 3 points, but you can't modify it. So surfaces are single-sided and oriented. The order that the points are specified in a triangle matters. The convention we use is that the front side is defined by the order counterclockwise? Oh, so this is a right-hand rule. Oh, yeah, okay. So everyone who has hands, if you take out your hand, point your thumb up, pull all your fingers into the palm of your hand, point your thumb up, and point your index finger outwards and your middle finger out of the palm of your hand, you get this 3-axis thing. And the gist is the direction of the palm is the right-hand rule. So, actually, can I just...
I learned it a different way, actually.
Really?
Oh, yeah, that first picture is actually really good. They're recommended by Pocket if you go back on your Google search.
Oh, yeah.
Yeah.
Yeah, I'm trying to
I
describe...
like the rotation version, right? Like, if you start at the x-axis and you rotate your fingers to the y-axis, then your thumb is the z-axis.
I mean, I like that, too. I'm not disagreeing with it.
It works for the left-hand rule as well, right? So
yeah. I was just describing how the order of the vertices describes the face, which we consider to be the front.
Right.
It's completely arbitrary that we do right-hand rule for this. It's just a good assumption to make. Pointing finger facing up.
Yeah, so I think like if you just start it, like if you count the points in order, like 0, 1, 2, and you rotate your fingers through those 0, 1, 2, then your thumb is in the front facing, right?
Oh,
and you don't have to think about this finger goes here, that finger goes there, right?
Okay.
You just do them in order.
That's a good way. Yeah, I like that.
Yep.
Thank you for mentioning that, because I was no clue how to describe that. I sometimes YOLO it and just go, well, if it's looking wrong, I'll just flip the order because I'm like, whatever direction it is, it's wrong.
Well,
So
there's like 10 different places you could get the ordering
yeah,
backwards. So.
yeah. When you have a single triangle, it's easy to flip a single point. When you have a whole mesh, it's not so easy. So this is a nice trick. And this Graphics Codex assumes a right-handed coordinate system. Another instance of the right-handers subjugating all the left-handers with their dominant hand. 50% chance of getting it right in any. Okay, so the triangle list is just a set of triangles known as a mesh. The unit cube that goes from 0, 0, 0 to 1, 1, 1 contains 12 triangles, 6 square faces, each comprising of 2 triangles. That is an extremely common. It's probably like the most common shape that people draw in a graphics API, aside from a single triangle, a cube. Like every time I've done any type of learning a graphics API, I end up making a cube. And so, yeah. I just, okay, so it's just talking about ways to structure it. Oh, yeah. Yeah, that's a good question. Question is to whether you make the origin touching a corner or the center of the cube. I always do -1 to 1 instead of 0, 0, 0, 1, 1. That's just my preference, because then the center of the origin is the center of the cube. But oh yeah, and then making the cubes go from -5 to 5, so its side length is 1, but so its volume is 1. But the corners are not on the unit on integer boundaries. Okay, a tetrahedron, yes. Okay. There's 3 triangles. Each 3 of them are axis aligned, plane aligned, and then there's one that cuts across X, Y, and Z axis to connect the 3 outer dots.
So I don't think that's actually a tetrahedron, right? Because a tetrahedron, all of the edges should be the same length. Right, and in this case, the diagonal edges there are square root of 2 or something like that, right?
It looks like he calls it a irregular tetrahedron here.
Yeah.
Okay.
Different face areas.
Yep.
Yeah.
That's technically
0. Yeah. So yeah, this is a irregular tetrahedra because it's not the same triangle size on all faces. It's 3 of them are the same, and then the 4th one is not, because the 4th one has to connect all the other 3. Okay, and so we have a mesh, we have some points. That's the mesh. Oh, this is just an array of points, and it's getting it from the mesh. And then we append our 4 faces. Yeah, this is just a bit of exercise to do the same thing but create a cube. This is actually a good list, a good exercise in general, especially for the orientation stuff, because then you have to figure out which order things are and making sure that the order that they're listed in will make it the correct faces point outwards rather than inwards. I've never heard of this.
I think this is just the code base that Graphics Codex use.
Yeah.
So they have a companion code base basically.
Yeah. Getting into the gritty detail of how many bytes are needed. I just want to look at this quickly. And it looks like a slightly different vector. So, median partition. Okay. Not gonna get sidetracked with it. Index triangle list. So one of the downsides of having only points be specified for the triangles is that, at least in a cube's case, a lot of the points are shared. 1, 2, 3, 4, 5, 6. At most, a corner has 6 shared triangles in it, depending on how you set it up. So that's the same point expressed 5 more times than actually necessary. And so the way we fix that is we use indexing. So we store a list of points and separately create a list of triangles around those points by specifying indexes. So here we have just the array point is a vertex array, and we have the index array. The index array, every 3 elements of the index array is a separate triangle. As we can see here, when we add a triangle to it, we int in. Oh, it's getting a triangle. It's getting a series of elements out of the index array, and then using that to index the vertex array to get the points, and then we return that as a triangle. And so t times 3 means that if you pass in 5 as t, it will be multiplied by 3 to get 15, because that's the actual index, and then we'll do 15 plus 1, and then 15 plus 2, because there are 3 successive elements of the index array, and then that's used as the index, that's indexing into the vertex array. That's kind of confusing to explain out loud. I hope y'all have mostly seen the index triangle list, or indexing index triangle list, this concept before, since it's not uncommon. This is a pretty good image for what it's doing. Okay. Yeah, so the indexes, but the actual points are over here, and then the indexes to use them. Okay. Yeah, and this is just, it's to create a tetrahedra, we add the points, and then we append the faces as we need them. And we can compare the size. It's a lot less. 96 for a tetrahedra versus 144. And then for a cube, we have 240 bytes versus 432. And the more common vertices in a mesh, the more savings you get, because the vertices are a lot more costly than the indices. You know, a triangle is 12 bytes, whereas an index triangle is 12 bytes per index, or per triangle in the index buffer. And then the what? Okay. Digital camera is a measurement device. It measures how much light, the amount of light striking each pixel, or each pixel of the sensor, and it's just a 2D grid. Then we can raster or synthesize light in the same pattern and reproduce it from the original scene. So rendering is a measurement problem. That's a phrase I've not heard before, but it makes sense. To produce require units. Yeah. So since we're measuring things, we got to use units. Ray of light. We propagate along a medium. You can only see your light rays that enter your eyes. Look like points. Oh. So our eyes are measurement devices, and if we think of light as rays, because we're at the end of that light ray, they're always end on to our eyes. Yeah. What it seems to be describing here is how the crepuscular rays, what we call God rays occasionally, they look like rays, but this is really just where there's a lot of light and it's hitting something in the air and causing it to bounce towards our eyes. But since it's happening in these God rays much more so than where they're not happening, they look like physical rays in the direction in these directions, which are not at our eyes directly. Mathematical ray is a point in a direction, one half of a line which extends infinitely in each. A ray is a point and a direction, and it extends infinitely in that direction, whereas a line extends infinitely in both directions. So, yeah. So while light travels from one surface to another, it's not infinite because it has a start and end. When we're computing things, we don't know where the end is until we've figured it out, so we consider it a ray from that perspective. Yeah. And then use geometry to construct the necessary segment. Okay. Transport paths. Points are described by 3 real units, points in the scene, as opposed to abstract mathematical constructs that have distance units, such as meters. P and X for position. Okay, so let P be X, Y, Z. Okay, so this is X of P plus 2 meters, so okay, that's interesting.
Is using lowercase p now?
I guess.
That seems like an odd convention to randomly change from capital to lowercase.
Yeah. Okay.
I think it's a capital P, but it's a subscript on the X.
Oh. Interesting.
It's like the X coordinate, and then the point P.
That is weird.
Oh yeah, if you look at the code, it does indeed correspond to that. P.X.
Interesting. So a line segment, you got 2 points, a start point and an end point. That's just a line segment. Great. Different amounts of light traveling opposite directions of the segment. Oh. Yeah. Since light propagation isn't perfectly symmetrical, so light going from one surface to another may not equal light coming from a surface to one. So a path is a collection of line segments, ordered set of points, implemented as an array of point objects. Transport path of interest for rendering object originate at a surface that emit photons. Interchangeably called an emitter, a luminaire, a non-natural source such as a bulb, or a light source. Yeah, so a source of light. Great. I think that's very highly descriptive. So now we actually define a vector. So geometric vector is the difference of 2 points, magnitude, and a direction. By convention, vectors are written in italic lowercase, okay, with a little hat on it of an arrow. So we have 2 points, B and A, we subtract them, and we get a vector. So their difference of the points has 3 components, the x, y, and z in the 3D. Carries distance units. A straightforward implementation is similar to the pointer class. From a data layout perspective, it's identical. A point and a vector are just differently typed. They hold the same data, which makes for fun debugging sessions when you confuse the two. Yes. This is not type safe, but that's okay. So this paragraph is just introducing what is also known as affine types, or an affine system. Affine math. Affine space, that's the word for it.
No, affine space is for like a vector space, but you can do some nonlinear stuff. So it's not this. I think affine type is the word you're looking for.
Does the Wikipedia have a different article? No, it doesn't. Okay.
It like preserves parallelism and something else, but not angles, right? Something like that.
Okay, this is getting way into the weeds. I could be mincing my words here, so I'm happy to be wrong. The gist is just that there are points and then there are vectors, and they are they represent 2 different things. Points are the points in the space, vectors are directions in that space. You can't add 2 points together because that has no logical meaning. It's like adding the location of New York and adding the location of Los Angeles together. What does that even mean? Oh, I couldn't tell you, because yes, I can take the GPS coordinates, but adding them together doesn't give me a useful value. However, I can subtract, Los Angeles and New York together, and I get a direction between the 2, representing the distance and magnitude, direction and magnitude between the 2. You can take a point and add a vector, and you can subtract a vector from a point, so p plus or minus v. And you can add vectors together just fine, same with subtraction. But when you have a system where you can't add points, but you can subtract them to get vectors, it's an affine something rather. Yeah, there's ways to make. Oh goodness. Okay, here we go. There's ways to make a type safe thing, and it pretty much is just you define a vector 3 class and you define a points 3 class, and they're just separate classes. Using type def is not it creates a weak alias. It's always interchangeable. Yeah.
Adding points can make sense in an intermediate sense. So if you add 2 locations and then divide the result by 2, we can get the average. The midpoint between the locations.
That's probably the only point there where you add point makes sense is to do some kind of interpolation.
Right. But I mean, what you're really doing, right, is when you subtract them, you're getting the vector, and then you're multiplying the vector by 0.5 or whatever, and then adding the vector back to the first point. If you were going to do it in a type correct way. Right?
I guess I should clarify when I say it doesn't have any logical meaning. It doesn't have any logical meaning in a vector space. If you take all the locations of, if you take all the points of something and then want to find the average point, yes, you could add them all and divide them by however many you have. That's just statistics at that point, not vector math. So, yeah. I mean, that's a fair point. I feel like that's 2 different domains of math.
So if you add LA and New York, you get Kansas?
Something like that. Pretty much. Geometric vectors are related to linear algebra vectors and general computer science vectors. What does that even mean? I'm going to continue on. Ignore it.
Like in C++, vectors is an array, basically, right?
I think that's just a word choice that some committee people decided on, and it's not really reflective of a general trend in computer science. Maybe I'm reading too much into Bike Shed. Anyways, yeah, a vector is an array of 3 values if you're talking about a 3D vector. And so you can just address any element and you'll get, X, Y, or Z of it. Yeah, we often overload the types to make it really easy to access individual elements because we'll want to access an axis and do something weird with it. Yeah, so you can add 2 vectors together and it's element-wise. Multiplication and division is the same premise. You just take the scaling factor and multiply each element of it. But the magnitude or length of a vector is the Euclidean distance between 2 points separated by that distance. So, you take the magnitude is a dimensionless value. Is that a word for it? You have x squared plus y squared plus z squared. So you take all of the individual components, you square them, which removes any of the positive or negativeness, because if you square a number, it's always positive. Then you add all those things together, and then you square root it to get how long it is. Yeah, Pythagorean Theorem. This is a squared plus b squared equals c squared. Is that the Pythagorean Theorem? I think.
Yeah.
Okay. That's like such a fundamental thing that I'm like blanking on. Yeah. This is not a proof for why the magnitude is this equation here. But it is that, so that's great. So here we introduce unit vectors, which is special in the sense that they have a value where the magnitude is always 1. They have values such that the magnitude is always 1. And unit vectors are useful because they do not impart a distance in a direction. They're always the distance of 1. So they're, because 1 times 1 is 1. A vector, a unit vector times another unit vector should have a magnitude equal. Is that valid? If you multiply 2 unit vectors, you get a third unit vector, just in a different direction. Or is that not right?
That doesn't sound right.
Yeah, that doesn't sound right either, but...
Because that would only be true if you multiplied...
You don't multiply vectors together, that's the problem.
Yeah.
Now that I think about it. You can add unit vectors together.
Dot product.
Yes, but a
dot
product doesn't give you a vector.
Scalar. Yeah,
Yeah.
it's only cross product. If you cross product two unit vectors, you get a unit vector back.
Yeah. Cross product is more like the right hand rule where you take 2 of them and you get the third one as a, orthogonal thingy. And cross products is weird. Like, it's special in different ways than the dot product is. And other magnitude and all that. So the process of creating a unit vector is called normalizing. And the simplest way to put it is you take the vector and then you divide it by its magnitude. It's like... what's an analogy for this? I mean, it's pretty much taking a magnituded direct... a vector with a certain magnitude, like say 5, and then dividing everything by 5 such that everything scales back to 1. And so normalization, you divide by this thing here. So if you want to substitute it, you take each element. So a function to normalize a vector would be x divided by x squared of x squared plus y squared plus z squared. then y is divided by the same thing, and z is divided by the same thing. Yeah, the unit sphere is the set of unit vectors that make a sphere around the origin. W hat is an element of S squared, or the unit sphere. So, yeah, S squared here means the unit sphere. That's a good thing to remember. Yeah, because we'll use it as an integration domain a lot. So the integral of something over S squared. Normalizing vector projects it from the original line instruction to the corresponding point on the unit sphere. Oh! Huh. That's a parallel I hadn't thought about. Not actual parallel, but like parallel line stuff. But like projection of a vector onto another vector. A normalization is a projection of one vector on itself onto the unit sphere. Okay. Geometric arrays. So we had geometric vectors, and now we're at geometric arrays. Geometric arrays have a point P, they have a starting point, and they have a vector direction. So P and W, is that W hat or is that omega hat?
Omega.
Okay, omega hat. Yeah. How many bytes does this array consume in memory? That is a good question. Unfortunately, I don't really care. For the purposes of our discussion here. Always describe the point in vector explicitly in both source code and equations. However, you'll soon want to transition to using a class of arrays in your render. So this text has the vector and point separate in equations and code, but then in the future it'll just be a single array class that is used, or array thingy. Okay, so the explicit equation for array with origin P and direction omega hat is how would you say this equation out loud? Because we got T is an element of R plus, so a positive reals, and that's put into the input to a function X, which its output is an element of R n times m, so n meaning a dimensionality factor, and m being the scaling factor, is equal to the point plus T times omega hat. Does that make sense?
No, not to me.
Is the M meters, or is that?
It might be meters. I could be. I was just thinking this was like I think this is meters. That makes more sense. I think the mx plus b is confusing me. I don't think they're using that m in that sense here. I think they're. You guys are right. It is meters.
What's R plus?
So the reals, real numbers, rather than fake numbers. The real number is a value of continuous quantity occurs at distance along a line. It's all numbers that.
Or is it only positive? Is that why it's plus?
I believe so. That makes sense to me. The reals are there was a picture with it that was a bit better than that one. So like natural numbers is 1, 2, 3, 4. The whole numbers are 0, 1, 2, 3, 4. And then integers are all the positive and negative whole numbers. You know, -5. Square root of 49 is 7, which is, I don't like this being here. That's very confusing. Rational numbers are things that can be expressed with fractions. This is not helpful because not all decimals can be expressed as fraction. Actually, can all fraction?
Yeah, they can. It's just divided by 10, right? But they can't all be represented in
Right.
binary.
Right. That might be computer science infecting my math mind. So irrational numbers, square roots that can't be expressed as a whole number. I mean, square root of 10 is not a whole number. And it's also like decimal numbers that continue infinitely, like 3.33333, infinitely long. Actually, no, that is rational.
The
True.
irrational should be a much bigger bubble because the numbers say that what is real is mostly irrational.
So all real numbers is saying is like, if you can write it down without the number I, it's a real number. Like we use pi here because pi is a transcendental number, which is a special. Does it have? No, it doesn't. Pi is special, but yeah, real is just kind of like any number that you can put on a number line. If you can put it on a number line, then it's a real number. Positive infinity, is that a number? No, it's a concept. Anyways,
No, infinity is not a number.
right, and not a number like nan, but just mathematically speaking, infinity is not something you can. It's not a number. Anyways,
Yeah, fun fact, all floating point numbers are actually rational numbers. Even though we sometimes call them real.
yeah, I mean, I've actually heard it described. Floating point numbers are actually little tiny ranges and not individual points. And I went, oh yeah, that is accurate. It's just the points, the ranges are so small for numbers between -1 and 1 that it's hard to find the limit without 1,000 zeros in the front of it. Yeah, square root of -1 is not a real number. There is no real number that will get you the square root of -1.
I think it's just an irrational number, right? Or is that
What are we talking about exactly? Sorry.
square root of -1? Huh. Okay, maybe
Imaginary.
It's a number. I can tell you that much.
maybe it's not real. Yeah.
Imaginary.
We've defined it to be I because it doesn't exist on the number plane. There's no, the quadratic. There's no solution to square root of -1 equals x. There is no real number that solves that equation.
Yeah, I guess they're complex numbers instead of real numbers. Yep.
And if we want to get into fun things, we can get into the not quadratic.
Quaternions.
Yeah, which is like the next dimension of complex numbers.
Yep.
Fun stuff. Okay. So that is our explicit equation for the ray.
What is the x corresponding to? So it looks like I'll try to use it as a point. Is that the case here?
I think he's making it x as a function.
Yeah.
T. I get it now. I understand this finally.
Did it have a thing above it for that?
I get it too.
Go back to the thing. I think it totally makes sense now.
So it's just x is the ray. Is that basically it?
Yeah, x is a function taking t, and the result is p plus t times the ray.
Right.
So
okay.
it's an implicit function, or not implicit,
Or-
explicit
yeah.
function for the ray.
Yeah. P plus t times the direction of the ray.
Oh, and when you put a t in, you get back a number, like a real number with dimension n. Yeah, that makes sense.
Yeah.
I guess the confusing part about that equation is we usually don't write domain and range in this kind of way.
Yeah, it's a little confusing.
I mean, normally we just do clamp from 0 to infinity for this, and then this is an output of saying, 3 out, XYZ output. So you'd return vec3 or something. But this is a mathematical formalization of that code. Okay.
Well, I think if it was math, they would also like move the t as a member of R1 outside of that equation. You know, like it's so
Probably.
really confusing.
Yeah. I agree, it is confusing. We can formalize light. Yeah, we'll put it in a tuxedo. Propagates along rays, so we'll measure the light at a point traveling in a direction. So light field L at a point and direction denote the light at P propagating in direction W. Omega. Use of L is historical. Okay. Multiple frequencies of light, but for now assume that L is scalar valued function. Okay. Lenoptic function. The 4D light field, aka light slap, and Lumograph. Whoa. Faraday. The general notion of a field of light was formally presented by Faraday in 1846. And even in Da Vinci's journals, he talks about it. These are words I've not seen before. Light slab, Lumograph, and planopic function. Can I just click the link? No, it doesn't. It didn't do what I... Oh. No, too far.
They have it. Oh, yeah, there you go.
Oh, okay, the Lumograph. Can I read this, or do I have to sign in? Okay, Okay, I think... Yeah, it's getting distracted. Okay.
Can we go back to the light field, the L? What intuitively is it just like, is it numbers in a field? Or what is that? I'm trying to think of how to think of that. What it is.
I think it's for like every point. Like if you had a point, you're at point P, then it tells you all of the light that's coming out of that in every direction, right?
Okay. And for every point, there's such number.
Right, and that's why it's a field, because it's over all of space.
Okay, got it.
Oh, yeah.
Just like a vector field or a electric field or whatever.
It's like if you wanted to discretize the light field, you'd cut it up into tiny little cells, voxel cells, whatever, and at each cell you'd measure the light in it, in either passing through it or whatever. In that case, that'd be like a vector field of light rays going through it.
This thing is actually like, I guess it's 5-dimensional, right? Or something in 3D space, because it's for every 3D point, it tells you the amount of light in every direction on a sphere coming out of that point.
Yeah, that is hard to conceptualize.
Yeah.
It's like a
5-dimensional?
Oh, sorry, because the vectors, actually, you only need 2 dimensions. You only need the latitude and longitude. You don't actually need all 3, right?
Oh, yeah, sphere. Okay.
Yeah. Okay.
And then the next stream of numbers is for colors? No?
For the position, right?
You mean in the W or the omega?
No, I mean, I was saying what you're talking about, the 5 dimensions of numbers. The guy first to the latitude.
The first 3 are where you are in the field, right, in 3D space, and then which direction the light is traveling, or where you're looking from.
Okay.
Latitude and longitude of where you're looking from.
Okay, gotcha. Nice.
Basically, like the continuous version of like light probes that are actually used, right?
I guess, yeah, kind of. I mean, yeah. Empty space is very useful because nothing is in it, so light can pass freely. So light conservation is an important concept. Conserved along array. There is no way for other light on different rays to get onto this one, and no way for light to leave it in empty space. For points x and p in empty space with no surfaces between them, the light leaving x in direction p must all actually reach p. Efficient rendering. Okay. So, because we assume air is empty for purposes of a basic rendering situation, we can look at only the 2 points on the surfaces that the light ray interacts with. And we don't have to worry about what happens in the middle because we assume all the light travel from one point to the other. And we don't have to think about or simulate all the points in the middle. This breaks down if you ever want to do volumetrics, where you have a bunch of air that is full of gas, crap in it, like smoke or a fog or all sorts of other things. And then you start having to consider all the points on the thing, and then things get more complicated again. But for what we're doing, we can ignore that case, I believe, in this basic formalization of light. And even if that was the case, volumetrics, you could probably start like reducing it into this type of situation where the step size is small enough. Maybe I'm talking out of my rear end. So the conservation of light along array formally is the light field where the point minus omega comma omega?
It's the epsilon. Like the
Epsilon is the smallest possible representable value, right?
Yes. That is epsilon, not this, which is the set theory element of that I was confusing it with. So yeah. The comma is throwing me off. Where omega is.
That's like the two arguments to the L, right? So it's P minus epsilon times the direction as your point, and then omega as your direction. Because they're just doing like the thing that you have to do in actual ray tracing, where you need to step away from the surface a bit.
Oh yeah. Okay, yeah, that's it. That's what they're describing. A little bit away from the surface, and then you're only considering everything between the two surfaces. Complicated and ambiguous. Foreshadowing. X to the point on the surface. If the surface is opaque and to visible light, then the light field is 0 for any direction because no light can flow through it. In contrast, X plus epsilon of omega is in the empty space, immediately both surface and prevents none of these problems. Although negated vectors make our parameterization clear and correct, there are also cumbersome notations that obscure the equality equation relationship. Some new notation makes our statements of light more terse and reveal important symmetry. Okay, let light outgoing from point X in direction omega LO X plus, and then the light incoming is X minus omega. So it's... Okay, what is this trying to describe?
I think it's like the light. Oh, sorry. The light coming off of the surface, you step away from it that way, and then when you're talking about the light and like hitting a surface, you have to step backwards along the ray.
I think they're actually talking about like different rays. If you were looking at the example picture, right, the omega is actually different for the outgoing, like it's the omega hat versus the incoming, which would be the one coming from Y.
Is it though? It has emitter over here, it has arrow pointing towards Y, and then Y pointing towards X, but then there's a ray of X pointing towards Y.
Yeah,
And
so
then
the omega hat is the one coming from X going to P, right?
You mean negative omega?
Like if you look at the to
Oh,
the
you
right
said
of x.
you said x going to p. I heard y, so that's
Yeah.
my bad. Yeah, okay.
I don't
So
think this actually corresponds to that diagram at all. I think it's just talking about kind of a neat point in any direction.
yeah,
Like if you're talking about a point X and you want to talk about the outgoing light, then you step off of X along your outgoing ray. And then if you're
yeah.
talking about point X and the light incoming, you have to step backwards along the incoming ray.
Yeah, because light is both emitted by a surface and absorbed. Absorbed may not be the right word, but there's light coming at a surface and there's light going away from a point on a surface, that is. So I think it's just trying to distinguish those two things because they're distinct phenomena in our formalization. And of course, we have to conserve the light, so the light going out must equal the light coming in. So that's probably why we have this thing here. Okay. Yeah. Yeah.
To be honest.
I think this is really just a lot of work to describe that the conservation of light.
I mean, it's not actually true. It depends on the surface, right? Like some surface absorb, and you're not always going to get the same output as the input on a surface. In the
It's kind of it's only defining the space that's infinitely small off the surface.
but he's actually going backwards in the Li, right? Like to the other side of the surface. So these equations are true in the void, right? In the space between surfaces, but not on the surface itself.
Isn't this actually? I think it's actually like it's saying that the light incoming to a point P from X
right.
is the same as the light leaving X towards P.
Right. So nothing got lost while it was traveling.
I think both
that
of those
makes
are
more
describing
sense.
the same
Yeah,
ray.
yeah.
That makes way more sense because light conservation, like a point on a surface, the light coming into it does not equal the light going out of it because the light might be absorbed by the surface and turned into heat, for instance, which we can't see as visible light and lose it, and so it's the energy conservation aspect of things is not being used here because it's not what we're describing. Okay. Yeah, I appreciate all this discussion because it clears up a lot of the confusion I have.
Actually, yeah, you can see in this diagram below, like the arrow leaving Y and the arrow leaving X. I think they're basically saying like those are the same.
Yeah, this arrow is the same as this arrow, but with an inverted direction.
Yeah, like the light traveling along that is the same for both of those.
Yeah. Hey, they got pinhole aperture in here. Virtual image plane, real image plane, yeah. Because cameras take photos upside down. Because of optics. Okay. The light leaving X and some fraction of the light entered X from Y and scattered here, plus any new light was emitted at X if the surface was glowing. So, there's a whole bunch of paths, and the paths that make it to the pixel on the sensor are what we're considering and what we want to compute. And because because the direction from X to Y, if the ray is invertible, is that the word for it? We can go from emitter to Y to X to the camera, and we can also go from the camera to X to Y to the emitter, and it's the same thing, the same ray. It's just we're traveling it in a different direction because of the.
I have a question.
Yeah.
If all the quantities are reflecting of the light are equal, wouldn't they just keep reflecting and then everything would be filled with light? There's no diminishing of light. Do you want what I mean? Like where it says equals negative omega I Yeah, right there. It equals the one that's at the bottom where it's coming out of X. It's coming out of Y is equal to coming out of X, but they would just keep reflecting everywhere, right? And
So this is not talking about what's happening at the surface. What it's talking about is the ray along the point between the surface, the ray between the surfaces at a infinitesimally small point away from the surface, traveling through free space. So you're right. It would, in your thought, you're describing a perfectly reflective surface. Nothing in the real world is quite like that. So all surfaces absorb light when they actually interact with it. But what we're trying to formalize here is the rays that are above the surface and going between the points. Does that make any sense?
Let me see if I can paraphrase this whole thing.
Yeah.
All he's trying to say is that when you leave Y and you move through empty space, the same amount of energy that left Y gets to X, right?
Yeah.
So if you go scroll up to the equation that he had, so it's actually two different points, right? This equation number 8 is from going from X to P, saying that if as you go along the ray from X to P, you don't lose any energy because it's the void. I think that's what this whole section was about, basically.
Yeah. It's a lot of work to say nothing is lost along the way in our current model.
good, I believe you.
LOX omega of OX is the sum of light emitted at X in direction omega O and light scattered at X in direction LOX. What? Did I just read? Let LE be the subset of light that is emitted. It will end up being trivial in the implementation of a renderer. Subset of light emitted. Okay. Light doesn't just reach X from Y. There are plenty of other paths that have XP as their final segment. So consider the light that reaches P after scattering at X. We have to consider all possible points for which light might reach X initially. So light out of X in omega direction of OX, which is the primary ray along our diagram, is equal to the light emitted from the light emitter. Is that the right word? No, is it?
That's like emissive surfaces, right?
Oh yes. I think that is the emissive surface. The light that X emits in the direction W of X. Plus all of the incoming light from every possible place that light could hit X and scatter towards the primary ray. Is that just a rendering glitch, or is that?
I think that's just because he hasn't introduced PRDFs yet.
Okay. Square ... is mathematical. There will be stuff here later.
Oh, it says that in the next sentence, actually.
Oh. Abstracts. How much light? I thought this was like a rendering glitch, because that box is the classic I don't know how to render this Unicode character thing I see.
I know, right?
How much light scatters at X and some measurement details about the integration. Domain integration is every point Y visible from X. We'll formalize both these short and fill in the box. I love filling in boxes. Okay, so all visible points. This is the integral. So all visible points towards X. You want to try to break down this box here to keep going? We're close to the end. Yeah, okay.
Well, I think I'd like it. I mean, it should be the integral over the S2, right? Over this
Yeah.
surrounding X times or instead of dy, it should be d omega. But I think he's somehow discretizing it, so there's only y sort of represents all the things that are emitting light towards x. But that's kind of an inefficient way to write it mathematically. I don't know.
Everyone have a different way to write rendering equation. It's like every book have different notations. So
yeah,
I guess in this case it should probably be like the big sigma, right? Like sum over every point.
This is visible points, implying that there is the barrier of the surface here. Only the things that are on the visible surface, meaning not inside the surface. But that's actually not that useful. Never mind. Okay. Well, let's see what they left out. Instant in time. Okay, so this says we assume light travels instantly, but some visual effects require you to integrate over time. Things like motion blur. If you're moving fast enough, the camera can't really perceive it because the light isn't perfectly clear. Yeah, there's phase because it's an electromagnetic wave. Well, since sunlight is pretty uniformly distributed, we just kind of, and light bulbs are too, we just kind of assume everything is irregular and don't need to model it. Okay, that's an interesting statement. Mirrors reflect in the way they do due to phase. We'll model it, but we will not do the low-level mechanism that makes it happen. Oh, okay, it's common in other domains. That makes sense. Yeah, polarization is what I was thinking of when it was describing phase. Yeah. We'll probably do the red, green, blue frequencies because that's what we can perceive as in our eyes. And does the Graphics Codex cover spectral rendering?
I don't know. Probably not.
Yeah. Okay. Okay, so there are reasons to use spectral rendering. I don't know if they use it. Yeah, there's a lot of symbols here. I'm getting flashbacks to the other series we did on the other renderer, and just trying to understand all the math they used to define everything. I think that's all we're going to cover today.
It's just good old rendering equation. It's exactly the same, using probably different symbols, but same stuff.
Yeah. Yeah, radiance transported through x plus epsilon omega I in direction of negative omega I, because the light in and then the light out is through x plus epsilon omega O in direction omega O. Oh. Okay, so here they're different omegas. It's the same point but in different directions. And then the flux, the power propagating through points in A directions. Can't remember what upside down L is. The Greek letter.
Lambda? No, it's not lambda.
I think it's gamma.
Really? Okay. Well, I'll take your word for it. And then we just have the basic points. Unit vectors, unit incident on light. Okay. And then we have the references. I think that's all we're going to do today, because the graphics one, the geometry one was super short, but then this one took a bit longer to get through. So, yay!